Let me share my screen. Okay, I hope the screen is visible. Okay, so let us continue our discussion. So today we will take a small break after maybe 1 hour or so. Okay. Yeah. And we will finish this discussion today regarding Fourier transforms, discrete Fourier transforms. So let us say I want, if we have time, we will discuss FFT algorithm also in brief. And from next week, we will start with Laplace transforms. Okay. All right. So we are discussing continuous time Fourier transform and its properties. So we discussed differentiation in time domain and frequency response and all that yesterday. So differentiation and frequency domain, yes, I asked you guys to go through it, and I hope it is fine. Okay, if you follow the previous derivation, yeah, this this should follow. So let me not do that because we don't have much time. So yeah, the example of Gaussian also we discussed partially. So one way we showed that yeah, so forward Fourier transform of Gaussian function turns out to be Gaussian. We did not do the converse, so I left that to you guys. But yeah, I can do it quickly. So one way we showed that yeah, if gt is Gaussian, then capital G of j omega is also a Gaussian. So let's try to figure out the reverse direction. So if we start with this, then we want to show that inverse Fourier transform of this function is a Gaussian function. Okay. So there is no question, then please mute yourself. Yeah, so we are going to use the same trick, okay, which we used to derive the forward direction. So we are going to differentiate in frequency domain now, this capital G of j omega. So we get similar sort of expression. Instead of t, we get omega here. There is a negative sign, and sigma squared is in the numerator now. And you just use the same properties. Okay, so differentiation in frequency domain is same as, so I'm saying about this thing. This is same as multiplication in time domain with this j factor and a minus sign. So this is in time domain, and multiplication by j omega in the frequency domain is differentiation in time domain. Okay, so yeah, this quantity in time domain is this. So since we are equating these two must be the same. And here now you separate variables. Okay, so uh, dg over g, you put that to one side, and yeah, terms in t, you uh, you collect them on one side, and then you integrate. So yeah, this is straightforward just from method of separation of variables, and then you take anti-logs. Okay, so g of t is g of 0 times e to the power this term, and g of 0 is yeah, this this expression. You just put t is equal to 0 here, and you get g of 0. Okay. So you recover g of t. If you go uh, if you go the reverse way. So I hope this is fine. So magnitude and phase response I discussed in brief yesterday, but yeah, I did not consider any examples. Okay, so yeah, went through this a bit quickly, but I hope you have seen at least one example. If not, then yeah, try doing this exercise. So this is Fourier transform of e to the power minus 80, and you can try to plot its magnitude and phase response. Okay, so this is its frequency response. Yeah, try finding the plot of this function also in frequency domain. So you plot it as the real versus imaginary as omega goes from whatever minus infinity to plus infinity, and you can also plot its magnitude and phase response. So its magnitude as omega varies is given by this expression. So from here you can see as omega goes to plus or minus infinity, this is going to go to 0, okay, because you have a 1 over infinity in the right hand side, and that is yeah, going to 0. Its phase response is tan inverse of omega by A. So this also you can plot as omega changes, and there is a minus sign because this is in the denominator. So you can plot these things, and you can plot multiple phase and frequency responses for different combinations of electrical circuits. So for example, you can try this type of electrical circuit. So you can have let's say some voltage source in here. So this is input, let's say V of I, this is R, this is C, and this is V of O. So this is my output, let's say. Okay. So you can first try to find what is V of j omega over Vi of j omega. That is the frequency response of this circuit. So this is an easy exercise. Okay, you should be able to find this. Write down the differential equation, then take Fourier transforms, and yeah, you can find the frequency response as well as the impulse response of this simple system, and then find its magnitude and phase response. Okay. So this is just one example. You can take different combinations. So put C in here, R in here. So CR circuits. You can put inductors also, LR, LC, RLC, various combinations. You can try those things. And if you don't want to do it by hand, yeah, you can also try this in MATLAB. Okay, so directly you just plug in these things and see what type of responses you get. So yeah, just play with this a bit to get some idea. And, see how their magnitude plots look like, phase plots also. Okay, so this is related to filters, yeah, which we will see a few weeks from now. But do try some of these examples. Okay. Then okay, so let me come back to this little bit later. Okay, so let us continue this these properties. Yeah, so central limit theorem. Let me come back to that little bit later. Okay, so this is quite easy. Let's recall integration in time domain. Okay. So suppose we are integrating our signal in time domain like that, and we want to find its Fourier transform. Okay, so if you go by first principles, yeah, it's a bit tedious. Sorry. Yeah. So yeah, doing this by first principles is very tedious, but yeah, you can use this trick of convolution. Okay, so this can be represented as xt convolved with u of t. Okay. So in the convolution integral, when you put u of t minus tau, yeah, your uh, upper limit is going to get chopped off. Okay, so so u of t looks like this. t minus tau going to look something like this. So that's why this convolution is same as this integral. And now you can use multiplication convolution property to find Fourier transform of this function y of. So that is just x of j omega times u of j omega, and u of j omega we have already derived. So yeah, you get this property. So this is integration in time domain.
Excuse me, sir.
Yes, yes, please.
So, but here the limits of here the limits of integration must be between minus of infinity to t, right? Or will it work for other limits as well?
Okay, so let me get the question. We are given this. Okay, so yeah, let me also write that here. So y of t, I am given that y of t is equal to integration from minus infinity to t of tau d tau, and we want to find y of j omega. Okay, so this is our question. We know this signal x, and this is integrated from minus infinity to t, and that gives y. So yeah, t could be anything. For each t, yeah, you evaluate this integral, and that's how y of t is obtained. And the question is, what is y of j omega in terms of x of j omega? So that is the question. Now, what are you saying?
So my question is,
There is an echo.
like the integration that we are finding.
Can you repeat?
So are you able to hear me?
Uh, yes, but sometimes there is an echo. So yes, please continue.
So my question is that we need to find this integral. So, but here is it compulsory to have the same limits, that is minus infinity to t? Because sometimes if we have to find 0 to t, let's say, so we can't use this, right?
Yeah, for 0 to t you cannot use this. This is from minus infinity to t, right? So if you are given y of t as if your question is this 0 to t x of tau d tau, then you cannot use that. Okay, the previous one. But in some cases you might. So if your x of tau is causal, okay, so x of tau, if this is 0 for t strictly less than 0, yeah. So if xt is causal, then yeah, these two integrals will be the same, whether you integrate from minus infinity to t or from 0 to t. It does not matter because yeah, this is 0. But if this is not 0 for t strictly less than 0, then these two quantities are not the same. So you cannot use them. So is that clear?
Yes, sir, got it.
Okay, so yeah. Okay, any more questions? All right, so let's move on. So Parseval's theorem, I hope you have seen it, but if not, let me know. Okay, otherwise I will not go through this again. So this is also pretty straightforward, and maybe I will just give a linear algebraic interpretation of this. Okay, so suppose I have a vector x and So I have an orthogonal matrix Q, and X maps to Q times X. So Q transpose Q is identity. So that's what we mean by orthogonal matrices. So now if you want to find norm of X or length of X, whatever, squared. So this is same as X transpose X. And what about this quantity? So if I call this Y, then norm of Y will be norm of Y squared. Y transpose Y, which is same as X transpose Q transpose QX. Let me not write all that, whatever. It is same as sorry. Let me write it. Q transpose Q. And again X. Since this is identity, these two are the same. Okay? So the length of the vector does not change if you multiply this by an orthogonal matrix. And Parseval's theorem is basically saying the same thing, but in infinite dimensional spaces. Okay. So here we are using Dirac delta basis in time domain, and here we are using exponential basis. So these are coefficients in exponential basis. These are coefficients in time basis, and yeah, the length of the vector or energy, whatever, that does not change, is what this theorem is saying. Because we are using orthogonal transformations, quote unquote orthogonal. Orthogonal transformations in infinite dimensional space. Because these are orthogonal functions as omega goes from minus infinity to plus infinity. Okay, so this is just an analogy. So you can always remember Parseval's theorem using this. It preserves length or distance. There is this 1 over 2 pi factor. Apart from that, it's basically saying this. Alright, so moving on. Yeah, this also hopefully you have seen. So yeah, this is like preserving inner products, but let me not get into those details. Okay, Fourier transform duality. So yeah, whatever you do in time domain can also be done in the frequency domain. Basically, what Fourier transform duality says. Yeah. So for details, you can refer to Oppenheim's book. Okay, so I think we have covered most of the properties, hopefully. Okay, so one thing regarding frequency response, yeah, again I forgot to mention is Bode plot. Yeah, h of j omega. So yeah, you can plot it as omega goes from minus infinity to plus infinity. This is called frequency response, and you can take log of h. Okay, so log to the base 10, and you can also take log of omega to the base 10. So Bode plot is basically this plot, log of the frequency response plotted against log of the frequency. Okay, so on the horizontal axis you have log omega, and here on y-axis you have 20 log h or whatever. You just write log. Those details are not that important. So I'm taking log on both x and y axis, and then yeah, you have a bunch of rules how this is being plotted and so forth. So I will not get into those details. Yeah, you can just read it from anywhere. Wikipedia is also a good source, and you have this Bode plot plotters. Okay, so yes, in MATLAB you can just type in a command and you can get this Bode plot. So So no big deal as far as those plots are concerned. It's just a log plot of yeah, the frequency response against the log frequency. Okay. So later, I don't know. I don't think we will get time to discuss this in detail, but yes, it's not a very deep concept or anything. Just a straightforward plot which you can easily read on your own. Okay. So have a look at Wikipedia page or just try some Bode plots in MATLAB, okay, using the command. Okay, so let me discuss central limit, but before that, let us discuss periodic functions and their Fourier transforms and Fourier transforms of train of impulses also. Okay, so periodic functions, yeah, recall that you can write them using Fourier series representation. So this is basically a Fourier series representation of a periodic function. Okay. So whether I take Fourier transform of x or Fourier transform of this, it is the same, right? Because yeah, if I apply f to the left hand side, then yeah, I'm also applying f to this term. So ak is just constant, so f will come inside and f will act on this complex exponential. So 1 times complex exponential is basically what we have in the time domain. Yeah, and we know the uh, delay or whatever frequency shift property. I forgot the name of that. So, yeah, frequency shift. Okay, so if you have a complex exponential multiplying your signal in time domain, you get a shift in frequency domain. So referring to that property, yeah. So we have 1 times complex exponential. Fourier transform of 1 is yeah, Dirac delta with a 2 pi factor, and this complex exponential will cause a shift in the frequency domain. Okay, and you have this index k going from 0 to infinity. So there is a typo. There should be a k here. Okay, e to the power omega naught kt. Yeah, so k is missing, and yes, for all k you will have a Dirac delta shift here. Okay, so Fourier transform of a periodic function are these Dirac delta impulses f, and the magnitude is scaled by this Fourier coefficient. Okay. All right. So I hope that is fine. So Fourier transform of periodic function is train of impulses, okay, with this magnitude. Okay, so let's use this to find Fourier transform of train of impulses. So what I mean by train of impulses is yeah, as follows. We are given Dirac delta functions and their shifts. Okay. So all of them have the same magnitude. Let's take it to be 1. This is called train of impulses. Let me not write it. And we are interested in finding Fourier transform of this. So this is a periodic function, right? Because yeah, this this is get this keeps getting repeated after whatever the period is, and we have the formula for Fourier transform of periodic function. Okay, the the only thing which is unknown is this coefficient a of t. We know everything else. Yeah. So what are these coefficients? So, yes, you just find Fourier series coefficients for train of impulses. So I have done that in here. You also must have seen this previously. So yes, if t is the time period, then yeah, just apply the formula to get Fourier series coefficients for Dirac delta function. You get 1 over t. So this integral, yeah, you just evaluate this complex exponential at t is equal to 0, which is 1. 1 over t stays as it is. Okay. So a of k is 1 over t. So just substitute that in that expression. Yeah. So ak is 1 over t, and that's all. So you get 2 pi over t times yeah, this train of impulses. So both in time and frequency domain, yeah, you have train of impulses. Period is different, but so this is in the frequency domain, this is in the time domain. Magnitude is also different. So here we took the magnitude to be 1, and here magnitude is 2 pi over t. Okay. So the shifts here are integer multiples of capital T. So that is our period in time domain. And here the shifts are integer multiples of omega naught. Omega naught is 2 pi over t. Omega naught is 2 pi over t. Okay, so you can notice one thing in here. If we try to compress this, so if t is small, then omega naught is going to increase. Okay, so if you try to compress them in one domain, they are going to expand out in frequency domain. So what I mean by that is if you have something like this in time domain, Dirac delta impulses which are very close, so t is small. What you get in the frequency domain is something like this, spread out train of impulses, and vice versa. If you expand them out in the time domain, you are going to get compressed Dirac deltas in the frequency domain. Okay. So this is again that uncertainty principle. Not exactly, but so yeah, this is also very important as far as sampling theory is concerned. Okay, so yeah, some of these examples, yeah, we will keep encountering repeatedly. So rect function, sinc function, train of impulses, exponentials, and things like that. Okay, so I think that's all as far as examples are concerned. So I will just make a short remark about central limit theorem, and then we can go to discrete time Fourier transform. So any questions so far? Let me see if there are any comments. All right, so good. Let us continue. So you might not have seen central limit theorem, but some of you might have, okay, in your probability theory. And yeah, let us see the connection between these two. And you can also play with this if you are interested. All right, so you can try this exercise for fun. Okay, so if you take a rect function, for example, and if you convolve with itself, you get a triangle like that. And you can keep convolving rect with its, I mean, okay, so this is the first step. Now you take another rect function and convolve it with this triangle function, okay, and keep doing that. So whatever you get, you convolve that with rect function. So we are just convolving rect with itself n number of times, and n is going to infinity. Like that. Keep doing this operation, and what you will see is it converges to Gaussian function, okay, as n goes to infinity. And instead of this, yes, any question? Okay, instead of rect function, if you take any other function, triangle or whatever, any function, and just if you just keep convolving with itself, you will see that it converges to Gaussian function. And the way to interpret this is in terms of the central limit theorem. Okay. So what central limit theorem says is the following: if you have n IID random variables, so first write that, and I will also explain what do I mean by it. So independent, identically distributed random variables. If you don't know about these things, don't worry about it. So each random variable will have some probability density function. Okay. So you can take it to be uniform distribution, which is like a rect function, or it could be something else. That does not matter. Okay. And if you have n IID random variables, so they are x1, x2 to xn. These are my random variables. And if I define a new random variable, which is the sum of these random variables, x2 up to xn, then central limit theorem says that the probability density function of y goes, I mean, yeah, it approaches Gaussian as n becomes larger and larger. And the way to interpret that in terms of convolution is as follows. So if I have just two random variables, y is equal to x1 plus x2, okay, just two random variables, then PDF of y, so how to write that, let me write PDF of PDF of y turns out to be convolution of PDF of x into PDF of convolved with PDF of x2. PDF means probability density function. Okay. This can be verified. Okay. So yes, from first principle in probability theory, you can show that PDF of this is convolution of these two PDFs. And if you have n random variables, then you get convolution of individual PDFs. Okay. So yeah, you can interpret central limit theorem yes, in terms of this convolution interpretation. Yeah. If we take a function and convolve with itself n number of times as n goes to infinity, we approach a Gaussian. That's what central limit theorem says, and you can also verify that using yeah, this convolution idea. So this is not a proof, by the way. Yeah, this is just an interpretation of this fact that of regarding central limit theorem. So that is just a small connection which yeah, those who are studying probability theory, yeah, they can interpret central limit theorem like that. All right, so let me not get into too many details of that. So I think that is all as far as this goes. Okay, so let's keep this in mind. Fourier transform of train of impulses, and let's use that to connect discrete time Fourier transforms using our understanding of continuous time Fourier transform. Okay. So we are going to sample our continuous time signals now, and we are going to see its effect in time and frequency. Okay. So the other thing which we are going to use is multiplication convolution property. So let's look at this operation. So this is basically sampling, okay? Multiplication of a continuous time signal by train of impulses. This is what we mean by sampling. So this is our continuous time signal x of t. So we want to understand discrete time Fourier transform and how it comes naturally. Okay. So this is our operation. I hope this is fine. Yeah. So you multiply this with train of impulses and you get these discrete impulses. So yeah, they are not, they need not be of the same magnitude. Okay, they are just this function x sampled at these time instances. So whatever magnitude of x is, that is the magnitude of these impulses. So let me show that in here. So x d of t, this is this discrete signal, this sampled signal, that is same as x of t multiplied with this this train of impulses. So that gives us x at these instances. Small t is equal to integer multiples of capital T times the Dirac delta function. Okay. So this is this sampled signal, and let us try to find the Fourier transform of this sampled signal. Okay. And let's see what do we get. So there are two ways to do that. Let us have a look at both of those types. So first type is as follows. So x d of t, we have this expression, and let's apply Fourier transform on both sides. So here we get x d of j omega, that is Fourier transform of this, and if we take Fourier transform in here, Fourier transform is going to act on this because this is a function dependent on time. This is just some magnitude. Okay. So we know that Fourier transform of Dirac delta is 1, and if you have shifted Dirac delta, you are going to get this complex exponential, okay, by this Fourier transform property. Okay. So xd of j omega is just xn times this complex exponential. And now if you put capital T is equal to 1, you are going to get x of n times e to the power minus j omega n. Okay. So you can recall this definition of discrete time Fourier transform. Okay, so I also have that here. Yes, where? Yeah, here. So Oppenheim has given another interpretation of how this definition arises, and here we are seeing another interpretation. Okay, so you can have a look at both of them. So this is Oppenheim's way of doing things, but yeah, you can also see how this definition comes very naturally. Okay, just by applying uh, continuous time Fourier transform definition. Okay, so I hope this is fine. Yeah, so this definition comes very naturally once you understand continuous time Fourier transform. Okay, so that is one way to write down the discrete time Fourier transform of this sampled signal. Now let's also use multiplication convolution property of continuous time Fourier transform to get another interpretation of this Fourier transform. Okay, so by multiplication convolution property, here we are doing multiplication in time domain, and we know that Fourier transform turns multiplication into convolution with 1 over 2 pi factor. Okay, so xd of j omega is going to be 1 over 2 pi and convolution of this with yeah, Fourier transform of this, right? So by that property, let me, so xd of j omega is convolution of x of j omega with yeah, Fourier transform of so yeah, Fourier transform of Dirac delta functions is 2 pi over t times the shifted impulses. So we have 1 over 2 pi turning multiplication into convolution. Okay, so that's why that 2 pi is going to get cancelled with 1 over 2 pi, and we are left with 1 over t. Okay, and omega naught is 2 pi over t. So I hope this is fine. So 2 pi gets cancelled. We are just left with 1 over t. This stays as it is, and I have written 2 pi over t instead of omega naught. Here again I am writing omega naught. Okay, so if you do this convolution, you just get x of j omega and its integer shifts. Okay, so let me draw the picture here. If x of j omega is I don't know, something like this. This is my of j omega, and I am convolving this with train of impulses. So what I am going to get is a periodic function. Okay, so this, and it's going to repeat itself. Okay, both directions. Yeah, and there are going to be overlaps also. So yeah, so if you convolve this with the Dirac delta at the origin, you get the same function, and yeah, once you convolve with its the shifts of Dirac delta, they are going to be overlaps. Okay, so yeah, this is yeah, this is x e of so what this says is basically this: discrete time Fourier transform is periodic extension of continuous time Fourier transform. What do I mean by periodic extension is, yeah, if you have a finite, not finite, if you have signal, I don't know, something like this, then periodic extension of this is, yeah, you just repeat it. It was not periodic to start with, but you make this periodic. This is what I mean by periodic extension. And it need not be time limited. So for example, it could go to, it has to die down at infinity, but it need not be zero, okay, after some finite interval like that. Okay, so if you do periodic extension of this, they are going to be overlaps. Okay, so yes, you are going to get some function which is not, the shape is almost the same, but yes, the values in here are going to change because it's going to uh, I mean its shifts are going to interact with itself, and you have to add them up. Okay, but I hope this periodic extension idea is clear to all of you what we are doing. If the signal is time limited to start with, then yeah, there are not going to be any overlap. But yes, the signals which don't die down at finite time instant, for those signals, they are going to be overlaps. So the idea I want to convey is the following. Yeah. So sampling in one domain leads to periodic extension in other domain and vice versa. And this property follows from multiplication convolution property and Fourier transform of periodic train of impulses. Okay. So any questions regarding that? In case I have not explained things properly, I hope this idea is clear to you. What's going on when we go from continuous to discrete domain, and when we try to extend signal periodically in one domain, it leads to sampling in the other domain. So I hope that is clear. So with this property, we can interpret various transforms with one another. So let me go to that remark to make this more clear. Yeah. So let us try to understand our four transforms. So we have a Fourier series, which is Fourier transform of, yes, I am saying Fourier transform loosely, so let me state that again. We have Fourier series for continuous time signals, continuous time periodic signals. We have Fourier transform for continuous time signals. We have discrete time signals, both periodic and aperiodic, and correspondingly we have Fourier series and Fourier transform in discrete time. So let's try to understand the connection between these four transforms using this sampling and periodic extension property. Okay. Alright, so let me start with this. So suppose we convolve a continuous time signal with a train of impulses. Okay, so let me not show that. So any ideas? What are we doing? We are convolving a continuous time signal. Let me draw that. And take some continuous time signal. Let me take it to be correct. We are convolving this with train of impulses. So any ideas? What does that lead to? Is it sampling or is it something else? So yeah, there are two options, either multiply or convolve. Okay, so yeah, we can take any function. So this could be any function, time domain. Yeah. So this is convolution and this is multiplication. So there are two options, right? We had seen two properties. So which operation represents which property? Yes, you might not have grasped this immediately, but yes, if you give it enough time, I think you should be able to figure this out. At least one of these. So anyone?
So convolution gives us periodicity.
Exactly. Yeah, because you are going to have shifts of this, yeah, at various multiples of whatever time period we have here. And what about multiplication?
So sampling.
Right. Okay. So this is periodic extension. Let me write that as E, and this is sampling. Okay. So if I convolve my continuous time signal with a train of impulses, I am going to get a periodic signal, right? And we know that we have Fourier series for periodic signals, and Fourier series coefficients are discrete. Yeah, they are not continuous in the frequency domain. So this is in time. And let us see what happens in frequency. let's look at the first case to start with. So this is going to have some Fourier transform, whatever. It's going to be a sinc function. In general, it could be anything. So let me draw sinc. But, yeah, it could be any function. So this is in frequency domain. Convolution is going to turn into multiplication in the frequency domain. Train of impulses is going to be again train of impulses. The magnitude will be different and the spacing will be different also. Okay? So if they are compressed in one domain, they are going to spread out in the other and vice versa. So if you do periodic extension in one domain, for example time domain, that is going to lead to sampling in the frequency domain. You're going to get samples of the sinc function, and that is consistent with what we know from our Fourier series. Yeah, Fourier series coefficients are discrete; they are not continuous functions of omega. Okay? So if you recall your Fourier series coefficients, yeah, they are discrete coefficients. Okay? AK, so this is discrete, and omega, whatever. So that is the first case. So this is convolution in time domain, which leads to periodic extension of signals in time domain, and that leads to sampling in the frequency domain. Okay. Now let's look at the other case. So we have the same signal in here, and we are now sampling in time domain. So in frequency domain, what we are going to get is the same sinc function. Multiplication is going to turn into convolution. Train of impulses are again train of impulses. Okay. So here we are going to get a periodic signal. So again, that is consistent with this that for discrete. So this is going to be a discrete time signal. Zeros outside this interval. And Fourier transform of that is going to be a periodic sinc function. Okay. So let's go one step further. Now we have, let's say, discrete signal. Okay. So non-zero over finite interval. And suppose we convolve this with train of impulses in time domain. So this is time. So we saw that, yeah, we saw two relations here. Okay, so I will tell you what are those two relations. We saw how continuous time Fourier transform is related to continuous time Fourier series, yeah, by this periodic extension property. And we also saw how continuous time Fourier transform is related to discrete time Fourier transform by this sampling property. Okay. So the only thing which is left hanging is the discrete time Fourier series. And, yeah, let's understand that to complete the connection. So if we convolve discrete time signal with train of impulses, we are going to get periodic extension. This is time and this is frequency. Okay. So convolving this with train of impulses gives us a periodic signal. Okay, discrete time periodic signal. Here we know that its discrete time Fourier transform is a periodic function, periodic sinc function, like that. It's going to get multiplied because convolution turns into multiplication. Okay. So this is going to lead to sampling now in frequency domain. So you are going to get samples of this periodic sinc function, and that is again consistent with discrete time Fourier series. It is both discrete and periodic. Okay. So continuous time Fourier series is only discrete. It is not periodic. What I mean is not periodic in the frequency domain. It is, the signal is periodic in time domain, but its Fourier series coefficients are not periodic. But for discrete signals, yeah, we have periodicity in both time as well as frequency domain, and you see from where it is coming from this property. Okay, so I hope that makes sense to all of you. If if you feel confused, then I'm sure if you just go through this once, you should be able to understand this. Okay. Why I am saying informal is because Dirac delta and Kronecker delta are different, but these ideas can be made precise. So with some work, which we are not going to do. So the only reason for saying this, calling this informal, is yes, continuous time Dirac delta and discrete time Kronecker delta, they are not the same. But yes, you can get around that singularity. Okay. So this is an informal way to sort of relate these four transforms. Okay. So any questions on that? Okay. So we are almost 1 hour. What I want, I'm not going to discuss all discrete time examples in detail. I think the essential ideas we have discussed. So briefly, let me mention some of these things. Yes, if you understand continuous time Fourier transforms, then this should be straightforward. For example, computing this inverse. Okay, so the idea is again the same. Throw away odd functions, and yes, for even functions, use standard formulas for these integrals. Okay, so look up this Wikipedia list of integrals, definite integrals, and okay, now our interval of integration is over 2 pi. Okay, so I think one of these will be used. Maybe this one, I think. So cos over this. Okay, so yeah, this property is what we are using. Okay. So just use those standard integrals and this follows. You need not do this also. You can just take this for granted. But if you like doing this kind of exercises, then yeah, you should be able to check this. There is no new idea. These things are also in the same spirit. Delta constant pair, constant delta, discrete sine function. The derivations are identical. So this is what I meant by recursion. Okay, you do it once and then the rest of it just follows by referring to the previous case. Okay. All right. So let me not do that in detail. DTFT properties, yes, one or two might be slightly different, but most of them are almost same. The only difference is yes, you have now finite intervals of integral instead of infinite intervals, and yes, it's more or less the same. And I'm sure you have seen at least some of these before. Okay, so I think this is a good time to take a break. Yeah, so maybe after the break we can look at fast Fourier transforms. So fast Fourier transform is, I'm not going to ask that in exams and all, but I think it's an interesting and useful topic which you should know. And yes, I will also make, I think, some remarks regarding sampling theory, uh, which we will need later on. So maybe I will make that right now and then we can take a break. So these questions you can give it a thought, okay? And later on we will address them. So let me mention a couple of things. So there is something called as band limited signal. What do I mean by that is band limited. So what I mean by band limited is in the frequency domain. So this is omega, and this is the magnitude response, let's say. Then over some finite frequency, or this cutoff frequency. Okay. So your Fourier spectrum is non-zero only over some finite range. Okay. So this need not be always symmetric about the origin. It could be something like this. Okay. So maybe somewhere here. Your cutoffs are something like this. So your magnitude spectrum is only non-zero over this range. So this could be, let's say, omega C1 and this is omega C2. Like that. So yes, your signal is okay, not signal. Your frequency spectrum is supported only over a finite interval. What do I mean by support? Is where I mean the range where it is non-zero, that is just finite. Okay, so these kind of spectrums are not band limited. Okay, which decay to zero, but yeah, they continue. So this is badly drawn, but so let redraw this. It can be something like this. Does not become zero. Asymptotically, it approaches zero. It may be finite, yeah, on the left hand side or vice versa, but yes, the spectrum itself does not become zero over a finite interval. So this is not band limited. Not, not band limited. So band limited means yeah, non-zero only over a finite interval. Finite interval of frequency. Okay. So some signals are band limited. Not all signals are band limited, of course, because if you, I mean, that follows from the uncertainty principle. If you have finite support in one domain, then you are not going to have finite support in the other domain. Okay. So if you have signals of finite time length, then in the frequency domain, yeah, they are not going to be band limited. So this is something you should know. And now the question is as follows. Okay. So the question is, we saw how to go from continuous time to discrete time. And can you come back? Always or in specific cases that I'm going to leave you to think about, and we will address this later on. Okay. So just give it a thought. Okay. If at all it is possible to come back from these discrete samples, can we recover the continuous time signal? If so, can we recover it every time? That what I mean by that is for all continuous time signals, is it possible to recover the continuous time signals from its discrete sample? And if not, then when can you recover and when you cannot recover? Okay. So give it a thought. Okay. All right. So with that, I think we can take a break. So let us take a break. Maybe I will discuss a little bit about filters also after the break, and then maybe in the last 40-45 minutes or so, we can discuss the fast Fourier transform. So let me stop sharing and let's meet after, I don't know, maybe 7-8 minutes or so. So 10-12 or something. Let's meet around that. Okay, any questions before we resume? I'll wait for 1 more minute and then we can resume. Okay, so let us start. I think we are running short on time. I wanted to discuss this example also. I will, and I don't know whether we'll get time for FFT, but yeah, anyway, let us see. Okay, so I want you guys to think about some more questions, okay? I mean, yeah, we will answer them later on, maybe after 2 weeks or so. But yeah, if you already give it a thought, then yeah, you will pick up things quickly later on. Yeah, anyways, okay, so recall, so this is what I want you to think about. We know that sync and rect form a Fourier pair. Let's say in time domain. And this is in the frequency domain. So this is band limited, okay, because yeah, it is non-zero only over a finite interval. Okay, so yeah, let me so these type of systems having this frequency response, they are called low pass filter because yeah, they don't allow high frequency components to go through because the magnitude response is identically zero after some finite cutoff. So yesterday also we sort of saw this. So I'm not going to explain low pass filters in detail, but yeah, I'm just giving you the idea. And I want you guys to think about like some of these things. So yeah, this is an ideal low pass filter. So I want you to think about the following. So we know that this is not stable. Yeah, this is not absolutely integrable. So if this is h, then mod of h is not finite, integrated from minus infinity to plus infinity. So that violates the stability. This is not finite. So the system is not stable first of all. Okay, so ideal low pass filter is not stable. So not stable. Is it causal? So yeah, you need not answer this right now. Just think about this later. Yeah. So we know that non-causal systems, yes, they cannot be realized in practice. Okay, so if you want to build a low-pass filter, you have to have a causal filter to build any actual real-time filter. Okay, so yes, if and we also need stable systems. I will explain later the importance of stability. So how do we realize this in practice? So these sort of questions, just give it a thought. Okay, those RC circuits, yeah, I was showing earlier. Draw their frequency response and plot magnitude and phase response and see what sort of responses you get. Does it look like a low pass filter, whatnot, and so on. So yes, you will have some partial answers and some ideas if you give this if you give these things a thought. And we will discuss these later. Okay. So just like low pass filter, yeah, you can have high pass filters, for example, which have cutoffs at high frequencies, something like this. At low frequencies, it is identically zero, and yeah, there is a cutoff at some large frequency, and yeah, you have a non-zero response in that range. Okay, and you can also have a band pass filter with a cutoff say over finite frequency. So this is, for example, a band pass filter. You can also have a band stop filter. So it is zero over a finite interval and non-zero over this entire interval. So things like that. So yeah, these we will encounter later. So it's better you have some idea about these things and just think about it. How will you build it? If uh, building an ideal low pass filter is not possible, then yeah, how will you approximate it? How to approximate it so that it is close enough to ideal, things like that. Okay, so yeah, this is something to ponder over for you guys. We will come back to these questions later on, maybe 2 weeks from now. Okay, so let me discuss this PDE example of heat equation. Yeah, I have put this up in one of the problem sets. So yeah, at least this example, let me discuss. So we will again discuss heat equation with respect to Fourier, sorry, Laplace transforms. Okay, so yeah, next week or maybe next to next week, at some point we will again encounter heat equation. So this is basically application of Fourier transforms to solve linear partial differential equations. So let us see how to solve this PD. Okay, so T is the temperature profile. So you are given some, I don't know, some material or whatever, some rod, which, so X denotes the position, okay, of wherever you are measuring this temperature, and T denotes time. So assume there is just one dimension in space. Okay, so maybe a rod or something. Could be tending to not infinity, but I mean, yeah, let's approximate something which is going off. I mean, idealize. It goes up to plus and minus infinity. And T denotes the time. So the heat equation is as follows. So partial of capital T with respect to time is half k squared. This is some constant. And with respect to space, we are taking d squared over partial of x squared. Okay? So this is what is called as heat equation. Yeah, I won't be able to derive this from first principles, but yes, I mean, I can look it up and explain it to you, but no need to get into those things. Okay, just take this for granted. This is given to us, and yes, it's not too difficult to derive this from first principles. You use conservation laws to derive this. But let's not get into that. And we are given the temperature profile at position x is equal to 0. So let us mark that maybe here x is equal to 0. We are given the temperature profile. So it is this periodic function. So the temperature profile is periodic in time domain. Okay, it is not periodic in space domain. Okay. There was so in position it is not periodic, but in time it is periodic. Okay. So my temperature yeah, profile keeps visiting itself. It keeps repeating itself in time. And period is given to be 1. And I want to solve this PD. Okay, so this is my initial condition. Yeah, and this is my linear partial differential equation. Okay, so this is Oppenheim 3.67, and we want to solve this partial differential equation. So let us see how to do that using Fourier transforms and Fourier series. So one hint is already there. This is periodic. So of course we know there exists a Fourier series representation of this initial condition. Okay, so let's write that down. So yeah, this temperature profile as a function of T, we can write that as this complex exponential a n times this will be determined by whatever function we have. So a n gets fixed like that. So this is straightforward. And now, yeah, this is not so straightforward. Okay, so we are assuming that the temperature profile as a function of both x and t, we can write that down as this this coefficient, which is a function of x times this complex exponential. So we are doing what is called as separation of variables. Uh, I mean, yeah, this kind of trick may not work for all PDEs, but yes, we are assuming that yeah, we are assuming the solution is of this form, and later on we will see that we do get consistent solutions. Okay, so we are assuming a specific form of a solution, and if it is not correct, then we would have arrived at a contradiction. But yes, if it gives us a sensible solution, then okay, you are guessing a form of a solution, and then you have to justify whatever you have guessed. Yeah, that is consistent with the problem. Okay, so we are using this trick of separating x and t variables. Yeah, so sort of decoupling them, and now assuming this form of the solution of the heat equation, we have to make this consistent with the initial condition, and this also needs to solve this equation, of course. Yeah. So two checks we need to do. First of all, this form of T actually satisfies this PD, and it also satisfies this initial condition. If we can satisfy those two properties, then okay, this is correct, and the guess. All right, so let us start. So first step is just plug in this guess into this equation, and see what constraints do we get. So this Pn of x is our unknown. Yeah. So on the right hand side, when we differentiate with respect to x twice, we are going to get partial of Pn twice. Okay, this is independent of x. So that's what we have on the right hand side. N goes from yeah, minus infinity to plus infinity. So this is component wise we are equating. Okay. On the left hand side, we are taking partial with respect to t. So taking partial of this with respect to t will pull out this Jn omega naught factor out. Okay. So this is that factor times Pn stays as it is. Complex exponential, yeah, we are cancelling that out. What about this 2 over k square? There is a half over k squared. Okay, we are substituting omega naught is equal to 2 pi over t. Maybe I am making a typo or something. Yeah, let me check. Okay, so there is half k squared. Yeah, right. So that half k squared from here, when you take it to the other side, it becomes 2 over k squared. Yeah, so half k squared, that is on this side, and that we are taking to the other side. Okay. next step we are going to substitute for omega naught also. So omega naught is 2 pi over t and capital T is 1. So omega naught is 2 pi. So we are going to make this substitution also later. Alright, so let's also use this initial condition. So we are given that capital T at 0 is this periodic function which is given by this Fourier series. So Bn at 0 must match with these Fourier coefficients. Okay. So Bn at 0 is An, and we are also given that Vn does not go up to infinity at the extremes. Okay, so of course, temperature stays finite at the extremes of this infinite rod. It does not shoot off to infinity. That is also given to us. So along with this initial data, we also know that temperature profile at infinity stays bounded. It is constant. Not just bounded, it is constant. Alright, so with these constraints, now let's solve for Bn. Yeah, if we are successfully able to solve for Bn, then okay, just we need to plug in Bn in here and we will get the solution of our field. Okay, so we have this second order differential equation for Bn, n going from, so for each coefficient. Okay. Alright, so substituting for omega naught, so omega naught is 2 pi, we get this expression. Yeah. So we have this second order differential equation. B squared represents the second order differential operator. Yeah. So this is, you know this. And the solution of this differential equation, this is an ordinary differential equation. So somehow we have managed to convert our partial differential equation using this Fourier series trick to ordinary differential equation, linear time invariant ordinary differential equation, and we know how to solve this. Okay, so we need to find roots of this this polynomial in D. So yeah, I hope all of you know this. Okay, so if plus and minus s, for example, are roots of this polynomial, then solution of this homogeneous ODE is some constant times one root times x and another constant times another root times x. Okay. So this is standard ODE. So roots, yeah, let's take square root of this. So this turns out to be 2 comes out, root of pi n stays, and square root of j is this quantity. So yeah, that you can verify easily. Okay, so this is cos of pi by 4 plus j sine pi by 4. So yes, some complex number 1 plus j and 1 over square root 2 will come out. Okay, so that simplification also we will do later. Okay, so we have this form of Bn now, and we need to determine C1 and C2, okay, from our initial condition and this constraint. If we are able to do that, we are done. Okay, so let us proceed. Okay, yeah. So we know that at x is equal to 0, this is An, and as x tends to infinity, this stays constant. Okay, so we need to look at these two expressions now. Okay, and there is this square root of n also. So n takes both positive values as well as negative values. Yeah. And likewise for x. Okay, so there are some complications, minor complications, which yeah, we will figure out. So let's write down the solution for n greater than or equal to 0 first. Okay. So these are our roots. If n is greater than or equal to 0, then square root of n is again a positive number. So yes, this is okay. All right, so let me justify this. So what I am saying is, if n is greater than or equal to 0, I am saying that C1 has to be 0. So we are taking n positive and we are saying that if n is positive, then C1 has to be 0. Okay, so why is that? Yeah. So yeah, these are the two roots, plus and minus s. So here it is minus s. So this minus s is a negative number. Why is that? Because yeah, this quantity is positive, 2 pi square root of pi by n, and we are taking negative of that. So yeah, here we have considered the positive part yeah, of this root, and here the negative part. And since square root of pi n is a positive number and x is also positive, there is no negative sign. As x goes to infinity, this term is going to go to infinity because the positive real part in the complex exponential. That's why C1 has to be 0 if n is positive. Yeah. C2 need not be 0 because this is going to decay anyway. You have some real part of this complex exponential also, but that real part is strictly less than 0. So just convince yourself, okay, by substitution, that what I just said does indeed make sense, and yeah, that should give you C1 equal to 0, and that means Bn of x for n greater than or equal to 0 has to be this. Okay, so my C2 is going to be An. Yeah, for each n, it's going to be An. Minus of s is yeah, square root of 2 pi n. This 1 plus j coming out of yeah, this term, and 2 over square root 2 will be square root of 2. Okay. So this is going to be the solution for n greater than or equal to 0. And yeah, by the same argument, for n less than 0, we are going to get C2 to be equal to 0. Okay, because now yeah, square root of minus n is going to be a complex number and there is going to be a sign change in here. So yes, by the exact same argument, for n less than or equal to 0, yeah, this coefficient has to be 0 because our temperature has to be finite at negative infinity also. Okay. So this is how you get these two solutions for n greater than or equal to 0 and n less than or equal to 0. For n equal to 0, you can get that you get an. So they stay the same. All right. So the next part is not too difficult. We are given some specific initial conditions and we just need to plug in these coefficients. Okay. So maybe I'll leave that as an exercise to you guys because we don't have much time. Yeah. You just figure out the Fourier coefficient from this D1 and D0 and D1. I will upload this in the notes section, and yeah, you should be able to figure out how we are solving a specific case. Okay. So to start with, the problem was given in complete generality. E was assumed to be periodic with yeah, some Fourier coefficient, and now some specific coefficients are given, and from that we need to figure out the temperature profile. Okay. So this is what I am doing here. Okay. So just go through this. I think you should be able to figure that out. So we have.
So here, how did you take period?
Sorry.
How did you take period?
Period 1 was given to us. Yeah. This was given in the problem. So you can take different period also. That will just change your scale factor. So omega naught will change, of course. It will be 2 pi over t, and wherever capital yeah, this temperature and period, they are different. So yeah, I think omega naught yeah, that will change it. Capital T yeah, period is different from t. Apart from that, I don't see any change.
Okay, sir. I got it.
So yeah, you can also try this for maybe generality. So maybe assume some periodic initial condition with period capital T1 or something, distinguished from this temperature, and yeah, should get similar. Okay, any other questions? I think it will be difficult to cover FFT in 20 minutes, but I mean, yeah, let me see what I can do. You guys have a class after this? Anyone has a class at 11? I think some of you might have classes.
Yes, sir.
Okay. All right. So yeah, I will do what I can today, and if later on, if we have time, maybe we can revisit FFT. So this is going to be very difficult to do within 20 minutes. So yeah, DFT sort of similar to the discrete time Fourier series. I will do DFT signals somewhere. Yeah. Okay. So let us understand what is digitizing. Okay. So yeah, this is going to be a bit quick, but yeah, don't worry. You can read off the notes, and yeah, this is not going to be in your tests or anything. This is only for those who are interested. So yeah, you can read it from the notes and try some coding exercises if you are interested. But yeah, if you don't feel like doing it, that's fine. Okay, so let's and digitizing. So we know that the continuous, discrete time Fourier transform is periodic in the frequency domain. Yeah, of course, it is discrete in the time domain. But yeah, a few minutes back we saw if we sample DTFT in frequency domain, we get periodic signal in time domain. Basically, we get DTFS relation. Okay, so digitizing is yeah, something which is slightly different from sampling, but yeah, let me see if I can explain it in 5 minutes. So what do we have in DTFS is yeah, periodicity and discreteness in both domains. So something like this maybe. Let me not draw too many. And so this is in time. So yeah, both periodic in time and frequency. And you can also imagine some envelope, okay? So some continuous time envelope. Like that. So we start with some continuous time signal, maybe we sample it, we get discrete signals, we take its Fourier transform, whatever, and then we sample the discrete time Fourier transform also, and yeah, that's how we got these impulses. And yeah, imagine some continuous time envelope, okay, from which these samples were obtained. Those envelopes will change because yeah, we have done periodic extensions and so on. So these magnitudes will alter. Okay. So, but yeah, we have some periodic envelope of this. Yeah, both time and frequency. Sorry. Quickly, if I can explain with this figure. So yes, in time domain, this was the envelope. We discretized it, which led to periodic extension in frequency domain, and then we discretize in frequency domain also, which led to periodic extension in time domain. Okay, and now this envelopes we are approximating by this piecewise constant signal. So all these signals are of uniform width in uh, time domain, and yeah, so this is we are approximating by this quantized step, quantized rectangles in both time and frequency, and these are basically this is what basically digitization is. Yeah, so instead of treating these discrete impulses just at the discrete intervals, you approximate the envelope by quantizing using these discrete impulses like that. Okay, so you approximate this envelope using these rectangles like that, both in time and frequency, and this is basically what digitization is. So I've done it uh, very briefly. I accept that, but yeah, I hope you get what is going on. There is of course going to be some loss of the original signal. Okay, this is not going to be exact representation of the signal we started with. In sampling, if there had no loss, in periodic extension, of course, we are losing something. There is going to be some overlap. So, yeah, the original signal is not preserved in the strict sense. But we are doing some sort of approximation, and it turns out it works well in practice. Okay, so although there is some loss of information, this digitization does help, because now you have signals which are periodic in both time and frequency. So you just need to deal with finite intervals. Uh, so representing signals on a computer, you cannot store infinite like signals on a computer, and you don't have infinite precision also. So that's why this digitization, yeah, there is no escape from this if you want to do these things on a computer. So the idea is, so if the signal is something like this, it decays to yeah, infinity, sorry, decays to zero, then yeah, you do sampling and periodic extension such that yeah, this I mean that period is long enough, okay, so that the distortion is as small as possible. Okay, of course there is going to be some distortion. You are going to discretize, and you are going to do periodic extension also, and yeah, then you are going to do this digitization, and there is going to be some distortion. But yes, if you do your processing carefully, uh, yes, you won't lose too much of your information. Okay, so yeah, with that hand wavy argument, what I'm saying is, yeah, so for these sort of signals, we have this discrete Fourier transform, which is almost the same as DTFS. Okay, because in both cases we have yeah, periodicity and discreteness in both domains. So DTFS and DFT up to some scale factor. I don't remember what exactly the scale factor, but yeah, they are like almost the same. So, yeah, up to some scale, yeah. And that simplifies things a lot. So all the infinite dimensional stuff, yeah, we have brought that down to finite dimensions, because for DTFS, so yeah, here I had explained that. I did not explain this in the class, but yes, for DTFS everything is finite. There is no infinity coming in. You have finite periodicity. You have signals of finite interval. So yeah, you have finite dimensional spaces, and yeah, you can just do linear algebra in here, and yeah, there is no issue of convergence or anything. So yeah, the same applies to DFT also. There is no convergence issue because you are just dealing with finite sums. Okay. All right. So with that short summary, let us start FFT algorithm. Okay. So let me show the formula for DTFS. Yeah. So up to scale, DTFS is almost the same as DFT. So this 1 over n may or may not be there in FFT, okay, or DFT. So we won't bother about the scale factor. Other things are more or less the same. Okay. So this signal, yeah, if you can write this in the matrix form. So for example, if I want to find A0, okay, at L is equal to 0, then this is going to be 1, and what I get is just x0 plus x1 plus x2 like that up to xn minus 1. Yeah, that's what we have here, column of all ones. And so when you take DFT of a vector, you have this matrix multiplying the time domain coefficient. So we have this big DFT matrix. Then we have time domain 0 dot of xn minus 1. So first row is all ones. Similarly, you can figure out what is the second row. Sorry. Okay. So here am I. Yeah. Now you want to find A1. L is equal to 1. You want to find. So plug in 1 here and just repeat this. Okay. So n goes from 0 to n minus 1, and this e to the power minus j omega naught, that you can represent by omega. Yeah. So when n is equal to 0, you have 1. When n is equal to 1, you have omega. N is equal to 2, you have omega square, like that. Okay. So this is how you get these rows of this matrix. So I hope that is fine. That is how you obtain this DFT vector from time domain. So this is in frequency, and this is in time, and this is our Fourier transform matrix. Okay. So this is just a matrix vector multiplication. Yeah. Then we deal with sorry, this is not DTFS, DTFT. This is DTFS. Yeah. So this is just multiplication with respect to the Fourier matrix. Okay. All right. So I'm not going to finish this today. Let me see if I can finish this in 15-20 minutes in the next class. So be it. Otherwise, we will do it. And then, so let's consider this operation, vector times vector. So we have n entries here. Here also there are n number of entries. So when you perform this operation, there are n number of multiplications, and there are n minus 1 number of additions. I hope that is clear. Yeah. You are multiplying n numbers and you are adding them up. Okay. So n multiplications and n minus 1 additions. So we say that these are order n operations. Okay. So we forget about the scale factor. This is 2n minus 1, but yeah, we just worry whether it is first order in n or it is quadratic in n and like that. Okay. So vector times vector multiplication, we say that that is order n operation because that is the number of operations we need. But if we have a matrix times a vector, then we will be doing this operation n number of times, right? This 2n minus 1 operation. We will be doing that for each row. So that's why this matrix vector multiplication, this is order n squared operation. Yeah. So I hope this is fine with everyone. Okay. So as n becomes larger, maybe 1000 or something. This is not very large, but even with n is equal to 1000, yeah, n squared is going to be, I don't know, 1 million or something. So this is going to be very costly, this operation, matrix vector multiplication, and there is no escape in general from this computation. For if you have an arbitrary matrix here, excuse me, any matrix M, then yeah, matrix time vector is going to cost you these many operations. So 1000 cross 1000. But if your matrix has some specific structure, then you can exploit that structure to bring this operation down, and that is what FFT is based on. Okay, so the idea is to exploit the inherent structure in the matrix and to bring this computation down from order n squared to order n log n. Okay, so we will see that the FFT algorithm brings down this order n squared factor to order n log n. Okay. So this is going to be much less than million. Okay. So log of 10 to the power 3 is 3, and you are going to have some 3000 or something. Okay. So yeah, if you exploit that structure, you are going to have much faster algorithms and implementation, and that's what FFT does. Yeah, applications are in image processing, and yeah, you can go through those sort of things in the notes, and problems that also I have mentioned some problems, and on Wikipedia also you will find a lot of applications. So things like polynomial multiplication and all that. I just don't have time to get, explain or mention all those details. So let me see in 2-3 minutes if I can quickly give you at least some glimpse of that, and then later we will continue. So let's look at this example at least. If we get started with this example, maybe that will help a little bit. So this is our FFT matrix, and yeah, this is 8 cross 8 matrix, and yeah, we are dealing with a signal of length 8. Okay, so omega is 8th root of unity. All right, so yeah, I'm running out of time. I don't think I can explain in 2-3 minutes anything regarding this, but anyway, let me at least take 2 minutes from you. Let me erase this. So we have this matrix times vector multiplication. So what I'm going to do is I'm going to insert a permutation matrix in here. So P is a permutation matrix which when multiplied from the right permutes columns of F, and yeah, when P transpose multiplying from the left, it permutes rows of X, and since P is permutation matrix, P transpose is identical. Okay. So if we insert P transpose in here, that does not matter. There is another way to look at this, which maybe I'll explain later. I don't have time, but yeah, one is good enough for now. So that is what we are doing in here. We are multiplying this Fourier matrix by a permutation matrix which permutes columns of the Fourier matrix, and this P transpose permutes rows of X. Okay. So the permutation matrix is chosen like this. Okay. So one followed by third column, so first column, third column, fifth column, seventh column, like that. So choose your permutation matrix such that it permutes this in this fashion, columns of the original matrix in this fashion, and it will also permute rows of X. Okay. So 1, 3, 5 and 7, these are the entries of X in the top half, and 2, 4, 6, 8 are the entries of X in the bottom half. Okay. F8, the Fourier matrix looks like this. And now, yeah, you observe this structure in this permuted Fourier matrix. Okay, here, so to start with, we started with 8th root of unity. So that's how f of 8 looks like. And when you apply this permutation matrix, you can write this permuted Fourier matrix yeah, using 4th roots of unity. And omega 4 is this diagonal matrix containing 8th root of unity. Okay. So yeah, this is the trick of exploiting the structure, and now you can do this recursively. Okay, so F4 similarly you can split it into F2 and like that. Okay, so yeah, this uh, I will explain this if we have time later on. This idea is what is known in algorithms as divide and conquer strategy. You have, I mean, those who have seen merge sort, they can identify this strategy with merge sort algorithm, where you divide your problem into smaller and smaller problems until you divide no further, and then you put up all the pieces together, and that is exactly what the idea behind FFT is. So yeah, I will explain this later if I have time, but yeah, you can just go through this if you can. So we divide our problem into smaller and smaller pieces, and then we uh, solve each piece recursively, and then we put all the pieces together. And in terms of matrices, we exploit this structure in the matrix to factorize the matrix. And once the matrix is factorized, we can exploit this structure to have fast matrix vector multiplication. Let me stop with that. I have already taken some time. Next week we will start with Laplace transforms, and at the end of the course, if we have time, we will do this. So if you have any questions, I'm here. But yeah, the class is over. Thanks for attending.